Just a few seconds.
No worries.
Okay, I think we can. Um, Let me. I think. I think I have. I have sent the email invitation. Um, yeah, yeah. I think. I think we can start.
Okay.
Yeah.
All right. Yeah, so I guess we'll be introducing dgress, which is discrete denoising diffusion for graph generation.
Mhm.
I'll also be going over LayerDAG, which is currently in preprint. And so this paper is a bit there are definitely some things that need to be worked on in the paper, but the overall idea seems interesting. And then lastly, I'll introduce training diffusion models with reinforcement learning. As like a way to sort of think about graph generation in a reinforcement learning framework. This training with reinforcement learning will be on images rather than graphs as compared to the other two.
Okay.
Um, so I guess briefly, basically this dgress is sort of introduced as a way to generate graphs via a diffusion model. So they briefly start by introducing what a diffusion model is with three main highlights. So they highlight the fact that the distribution should have a closed form to allow for parallel training. They also want to have a posterior with a closed form so that we can use it as the target. And then
The
they,
first thing, Zach.
Mhm.
So, their graph generation is generating the graph structures, or assuming the graph is fixed, it's just generates the node features. Or
um, So they are going to be generating, so I'll get into that in a second, but yeah, so they're basically going to be defining a space chi and epsilon where x exists in chi uh, is the uh, node class. So this is going to be, and then you have an edge E that exists in epsilon that is uh, an edge class. So
Mhm.
both of these are going to be a discrete distribution that they're sampling from.
Oh,
Um,
so basically they're gonna generate nodes and edges, different
yes.
types of nodes and edges.
Hmm.
Okay. Well,
So
yeah.
yeah. Um, yeah, so the only reason why I'm introducing these three things is because they need to define them in order to efficiently sample these nodes and edges.
Mhm.
Um, So the key trick here is that they're basically being able to represent the noise as a transition matrix, um, which I think it goes into it later. But basically, they're using a transition matrix to show that if you can start from a very noisy, or you can start from a one graph and you can slowly transition using this Q function to transition forward in time. So they've essentially declared that you're going to have a random graph at time t. It's going to be completely random.
Uh-huh.
And then we can define a transition matrix, let's say QT that transitions from G to GT minus 1. And we can continue this till we get G naught, which is our ground truth graph, using the transition of Q1. And then we can define the overarching Q transition as this to be the Q bar of T, for which they can show that Q bar of T is actually just equal to the matrix multiplication.
So their denoising is kind of like multiplication. It's not like adding some noise or subtracting some noise.
Yes, but they're going to assume that it's of a certain type of noise, that is a categorical distribution. And it makes it so that the you can sample these graphs during generation. However, you're going to be sampling them from basically random noise, and the noise is going to be parameterized by a certain distribution.
How is the transition matrix defined? What's the size of the transition matrix? Is the number of nodes multiplying with number of nodes?
So if we look down here, the transition matrix, so they've defined the transition matrix to be the probability. So we have Q of xt. Sorry, I'm going to be writing basically this. That's big. Basically, I'm just going to be writing these lines right here.
Okay.
Where we have Qt of ij is equal to the probability basically of x at t is equal to j given 2 minus 1 is equal to I. Right? So this is going to basically just be showing that if we were to take the full edge matrix, or node matrix X at t minus 1, and we multiply it by our transition matrix for X at time t, this would we're going to make this is going to be equal to, whoops. Oh. So we have, I'm just gonna write this. So we have Q of graph T given graph T minus 1 is equal to our graph of our nodes at T minus 1 times our transition matrix QT for X, as well as our edge matrix time at T minus 1 times our transition matrix for our edges at T.
Oh, I see. So basically, it's the QX is kind of like the transition of the node types.
Yeah.
And the QE is the transition of edge types.
Mm-hmm.
But then how do you specify whether a node should be present or should disappear, or whether an edge should be present or disappear?
So this is just done by sampling from it, where it's, I don't know. So so we have a probability where we can specify if the probability, basically, when we look at this discrete distribution, if the probability is less than 0, or a value that's equal to 0, we basically assume it doesn't exist, or we say it doesn't exist. And typically this would be a problem because the diffusion model is not sparse. However, we're going to define a distribution that adds sparsity to the matrix.
Here it means let me think about. So this one is like so Q is the Q matrix. The Q matrix is a noise, as you said.
Um,
Right, you're gonna sample a Q matrix, right?
yes. I'm sorry, I'm just double checking to make sure. Yes, the Q matrices are noise that we can sample from. And we have other definitions for it further down of different ones. But yeah, we'll sample our Q. I believe we'll sample the Q matrix to generate the forward pass.
So the Q matrix is a probability matrix, right?
Yes.
Q matrix is a probability matrix. That means your next graph structure will also be sampled from the transition probability so actually you're going to base your samples of Q to generate your sample of graph.
Yeah.
So at the beginning, okay, and then, but at the beginning, what is the Q? At the beginning, the Q isn't a transition matrix, right? Or
Sorry, where?
I mean, at the very beginning, because if you do the generation process, you're gonna generate a random graph at the beginning, right? According to Q. But the Q at that time is not transition matrix, or you're just by default assume it start with say xt x0 equals to some default class.
Yeah, we assume x0 is equal to our target.
Okay.
And
then
then
you random sample every time you just random sample Q.
yeah, and so
And
then we have x1 is just equal to q1 x naught.
I would say x1 is sampled from
Oh yeah, so
uh,
yes, so this would be a
Q1
normal.
conditional x0, right?
Mhm. Uh, um, and then this should be some, I forget what goes here. I'll put that for now. I don't think this part is right. I forgot what goes there. Okay, so
Okay, what's the what's
sorry.
alpha t, beta t, and
So this is sorry, I've skipped ahead a lot looking for that, but we can get there. So okay. Yeah. So does this sorry, to start with this does this process make sense?
yeah, it makes sense. I just want to know a little bit details. So basically, they are assuming the maximum number of nodes is n, right?
Yes, they assign some cardinality to x.
Yeah. That means
And
you cannot generate a graph with more than n nodes,
yes,
more than a given cardinality.
yeah,
And then you kind of randomly generate any subgraph. And well, it's just a graph like with less than or equal to n nodes and also any edges between them. But how do they sample yeah, so q gt given g t minus 1 is xt minus 1 times qxt. Now it makes sense. So basically this xt minus 1 times qx given t actually take up just one column of the Q matrix, right? Because you're given like suppose it's like, okay, you're given xt minus 1 all the nodes at step t minus 1, the class of every node, right? And I don't know why. I think it should be like a qx. Oh, okay. If you use xt, if they represent xt as like one hot encoding, yeah, that probably is the case. Then you multiply xt minus 1 with qxt on the right. Okay. But then the E stuff, isn't the E stuff also determined by, they have to make sure that say after you change the node type, like some node might disappear, right? And then you can't have like non-zero probability from a disappear node to other node. Right? Hi Zach, can you hear me? Looks like, can anyone hear me?
Yeah,
Yeah.
Okay. Hi Zach, I don't know, I can't hear you. Oh, okay. Uh, yeah, probably while we while you're fixing your problem, maybe can you put some algorithm table so that we can take a look at the procedure. Yeah, okay, I think this one. Yeah, the algorithm one. Um, Chitung, regarding your question, so so here their noise is just a transition probability matrix.
Yeah.
Yeah, every time, yeah, they generate a probability matrix, and then using that to sample the node types and also the edge types.
I think the question is like if they use the cross entropy, so isn't this gonna push the like other probability like to 0?
The use cross entropy, I think it's very natural, right? Because every time, like you can imagine, like they generate they can sample their noise is just a transition matrix, right?
Yeah.
When they do the multiplication with the initial state, they get what they generate, and then they want to look at what's the difference between what's the difference between the actual graph, the actual sample of the actual example of the graph, and your probability, right? So it's very natural to apply the cross entropy to measure this because px and then pe, if you could say, um,
I
just
think the question
represent.
is like, so that should be continuous, and we force them to go to discrete.
Yeah,
and they
so so if you look at like this phi theta GTZ is just multiplying x qx transpose and those kind of stuff, right? And then they threw them into I don't know what's this phi theta. Maybe this is just neural network. You got some probability. The probability vector for the nodes and the probability vector for the edges. Then you just look at the x is the actual graph, actual nodes and their types, and the E is the actual edges. So they just calculate the cross entropy.
I see. Um,
So you see that in addition to their G prime GT, they also have some like Z. Okay. So okay.
yeah, I think the problem for me is like if they use cross entropy, I know that's the only one we can use for like discrete, but that like loss objective is gonna force the probability of others to go to 0. But like indeed it shouldn't be like this way.
So I mean there are other there are alternatives to the cross entropy.
No, I think that's like I don't think there's alternative to cross entropy, but I think maybe like so I think for me the natural thing to do is like use like the concrete distribution, because like if when they push the other like let's say the other probability to 0, that's an overkill.
Oh yeah, okay. Yeah,
Yeah, I
probably.
think if you're using like concrete like distribution, like they still gonna like that is a better objective than cross entropy.
Yeah, it's possible. Yeah, it's
Like
possible.
like a 3-through estimator.
Yeah, yeah. Yeah, Zach, one thing is that I was curious to know like how do they so GT if you look at algorithm 1 here, like GT is sampled from X times this guy. So this guy has already been a graph, right?
Yeah. So that's just the X is just denoting that as those are the two matrices that are defining GT.
Okay. And then they kind of extract some features, right? You see Z, this F, I don't know, maybe some kind of neural network, right? To get Z.
Yeah, F is not a neural network. They have a list of features they extract from the graph.
From the graph.
Yeah, so these are predefined functions that they have for the graph.
And then what is phi theta?
So the phi theta is the neural network. They have a special attention-based neural network they've designed for this problem.
And then the px, I guess the p hat x is the probability vector for every node type, right?
Yeah.
And p hat e is the probability. Is it just like softmax vectors for the edge for all possible edge categories, right?
Let me just scroll down. I believe so, but it is they might take a softmax of it before sampling, but it's just mapped by a linear layer, I believe. But yeah, there should be a softmax or something on the end.
Okay, I think it's a pretty interesting work. The let me think about. So how do they sample? Then how at every step how do they sample Q?
So Q is okay. So this is the weird one of the things that they alter is they choose a specific type of noise model for it. Where rather than so I guess starting with in the first paper for discrete denoising diffusion probabilistic models that they used, they start with a uniform distribution.
Mhm.
And this paper suggests that starting with a uniform distribution isn't necessarily the best choice. Where if you start with a distribution that is closer to the goal distribution, you're going to improve the model.
From what distribution?
So rather than doing a uniform distribution, they are going to,
Oh, they have some optimal prior distribution.
yeah. So they're saying you can find an optimal prior.
In what sense do they mean optimal?
Yeah. So they define they have this theorem where they say if you consider the class for which they've defined this graph of distributions over the graph that factorize the product, you can find these marginal distributions, and then these marginal distributions are basically an orthogonal projection onto the class. And then so that means that they claim that this means that they can choose a prior distribution that is close to the true data distribution.
So what's the okay? Then how do they get this mx prime and the me prime?
I don't know if they say they. Let me check here. So I don't actually know if they say.
Yeah, I'm kind of guessing. I'm kind of guessing they just look at their graph instances, right? They have a data set. Each data point is a graph. They just look at the empirical marginal distribution of every node.
Mhm.
It's a but it's a little bit weird because if you do the transition, you have to assume you know the number of nodes, right?
Yeah. Well, I mean, you have to know the max number of nodes to define the matrix.
Oh, so if you look at under equation 6, they said with this model, the probability of jumping from a state I to state J is proportional to the marginal probability of categorical J in the training set.
So it is just the marginal distribution of a class in the training set. Okay.
Yeah, but yeah, it's still a little bit weird to me because this relates to oh okay, let me think about that. Okay. Because this is all about the transition between different categories.
Yeah.
Oh, okay. Then it's doable. You can just estimate. You just count what's the ratio of categorical J in the training set.
Mm-hmm.
Okay. Yeah. Can we go back to algorithm 1 and say what's the generation procedure? Okay. So start from the random graph, and every time you're gonna get the features, and then through some attention mechanism, you got the edge, and you got the node per node class, and the class distribution for every node, and the edge class distribution for every possible edge. and then okay, and then you got some like posterior distribution.
Mhm.
Then you resample GT minus 1. Okay. Why it is called posterior distribution?
Why? Why do they call this the posterior?
Yeah.
Um, I believe this is what they're saying.
But their PRX is so their PRX their P hat RX comes from the noisy, right? You kind of like corrupt
This P hat IX.
yeah.
Um,
So can we go to the algorithm 1 again? Oh, okay. So okay, every time okay, it's based on GT minus 1. Yeah, I'm a little bit confused. How is the training? How can we say the sampling procedure is kind of reversed procedure of the training?
So, so it should be because okay, so I guess first, does the fact that we're doing this outside of a for loop make sense because we have a closed form for our t values?
Yeah.
So we can do this for an arbitrary t step. And then we have the closed form of the posterior distribution by Bayes' rule here.
Oh, so that one, okay, so that phi network is more like a denoising network. Like you have a noisy state, you have a noisy graph there. It tries to recover the true graph.
Yeah.
Oh, okay, it's okay. It's not recover noise. It's just is recover the original graph. It's like DDIM.
Yeah. Yes.
Okay. Yeah. Can we go back to algorithm 1?
Mhm.
So yeah. So you see, GT is a corrupted. GT is a corrupted noise, right? So X and E are some kind of instance. It's some kind of data, some graph, some particular valid graph from the data set, from the training data. And then you first corrupt it by multiplying Q bar TX and Q bar T and E. You got a noisy graph. And then throw some phi theta. I don't know, it's a graph neural network or some graph attention, whatever. It's gonna try to recover the original graph. But it's I mean, this recovery is reflected by P hat X and P hat E, right?
Yeah.
And then their loss is cross entropy loss, which evaluates how well your probability distribution matches the true graph, the instance of the true graph.
Yep.
Okay. So when you do the sampling, This one is kind of a sample from random graph. And then that's why every time you try to recover something, and then you use recovered graph to generate the next one. But what is qxi t minus 1 given xi equals to x and xi t?
Sorry, which line?
I mean, this one, when they compute the posterior,
Mhm.
where is this probability from?
This should be built from the prediction of phi theta. Let me find the. Um, I thought E theta is just equal to Q, is what we're trying to approximate. So we can just directly replace, no, that doesn't make any sense.
Yeah, that p theta xi. Oh, okay, so they choose p theta as something like this, right? Well, where does this qxi qxi t given xi equals to x, where does this come from?
This is the noise. So this should just be the previous state.
Okay, so you mean it has to sample Q in the denoising procedure as well, right? But in some step it doesn't show that. You should sample some Q, right?
If we have, so Q,
Yeah, Q should be the noisy transition probability matrix, right?
yeah, I'm just wondering, because if you have, because we have the previous one, so, because yeah, so our Q is sampled right here. So we sample our initial Q here, and we sample our QE here. And then they're missing the part where we then take our graph T, we have our graph T minus 1, which is composed of QX and T minus 1. Oops. And QE n of T minus 1. And these should be reset after each step.
Yeah.
We should be setting those to be our Q values for our next one.
Yeah, they should sample this noisy transition matrix, noisy transition probability matrix every time. It's
Yeah.
just like a continuous version, like denoising process. Although every time you kind of like get some like estimate of the true image, but you're gonna still based upon the noise to sample the next one.
Yeah.
Yeah, my question is that how do they make sure that this noise is to become smaller and smaller?
They have their alpha scheduler, which should decrease their noise over time.
Oh, they have their alpha scheduler reflecting in
Ye-
Q.
Yeah,
Oh,
so their
actually,
Q is,
oh, okay. Oh, yeah,
yeah,
makes okay. Yeah, everything makes sense. Okay, because because in the DDPM process, you have some like alpha T stuff, like making sure when T goes to larger and larger, alpha T approaches one, right? Or in other words, the other directory, you're gonna make it your when you proceed, right? Your noise should be small, skew should be smaller and smaller.
yeah.
Oh, okay. And also there is a chance that so can you go to the definition of their transition probability? That yeah, go scroll up.
This one or
Yeah, scroll up. Oh, okay. Equation 5, equation 5. Okay, so basically, so it's possible that some Q transition probability matrix, some entries are 0.
yeah.
Then in that case, um, does that mean like the node will disappear?
Yeah, well, so if so that would just be one value in the distribution. So there would be chances that certain classes of the node would not be possible.
Oh,
Um,
oh, okay, okay. But doesn't this mean like uh you're always sampling a complete graph? You're just changing the node type and the edge types.
yeah, yeah, you can see from this, we start out with like a certain graph and we're slowly changing each node type and edges that connect it.
Oh, okay, okay. It's always 6 nodes, right? It's always 6 nodes, but you can
Yes.
do an edge type. Like for example, edge type 0 just means no edges.
Hmm.
Oh, okay. But it doesn't have maybe yeah, there could be some heuristics like say for node type 0, it just means this node doesn't exist.
Yeah, you could do the same thing for the node classes as well.
Oh yeah, okay. Yeah, that would be very interesting, right? Do you try to follow their vision?
Of the discrete
Yeah,
of which,
version. There should be some correspondence to the DDPM derivation.
so this yeah, so the whole discrete denoising diffusion model is its own paper right here. That I need to read through this one and follow this exact how they do it. They gave a very brief um like
Also, this graph generation paper is following the discrete diffusion paper.
yes. Yeah, they're
Oh,
just applying it to a graph problem.
yeah, that's very interesting. That's very interesting. So yeah, you should follow the derivation.
Okay.
Because I kind of feel that we can use some like similar process to generate an expression tree, right?
Yes. Yeah, I think it would be it depends how lenient you want to be with the generator. But if we wanted, we could already use it to just in our CAD-SR model.
Mm-hmm.
Like we don't need an edge graph because our edges are predefined based on the nodes.
Mm-hmm.
And we already have our node locations, so we could continue a very rigorous like ordering of it.
Mm-hmm.
And basically just all we would have to do is sort of change our model to take in some additional information about the graph as well as the diffusion step. and it would basically just fit directly into our architecture.
Yeah. Yeah, that would be very, I think that would be very cool if we can do that.
Mm-hmm.
Yeah, very nice. What's the performance? How do they evaluate their performance?
So they evaluate their performance mostly on molecule generation and general graph generation. It's a bit weird how they compare it. For instance, they compare it based on how often they generate a valid node, a valid molecule, and how unique the model is based on their overall generation. And then they have several more metrics that I don't fully know what they are.
Oh, by valid, they mean, what do they mean by valid molecule? Do they
Um,
molecule is
yeah, there's chances that
well,
yeah, they could generate a non-realistic molecule.
yeah, it's very similar like Da and Zhitong. You two should be aware of this, right? We use diffusion model to generate a physical system state which supposed to satisfy some PD, right?
Yeah.
We also check whether our generation is valid, but simply by checking whether it satisfies some PD.
Yeah.
Yeah, that would be very useful because in practice there could be many categorical data. If we have some like generation categorical diffusion process, that would be convenient. Okay, is there any other things, Zach, you want to emphasize or highlight from this paper?
I think their architecture is a bit interesting.
Okay.
So to start with, they just use a whole bunch of these graph transformer layers, as well as they have special features and structural inputs. So this is a set of equations. It might be just down a little bit, where they're just extracting some information about the graph based on the adjacency matrix, and or like how the nodes are categorized. I don't exactly understand how they came up with these.
Oh, that's crazy, right? So
Yeah,
the multiply, so A is a adjacency matrix, right?
I believe so.
So it basically says they're gonna multiply A for 3 times is it's kind of aggregating like 3 hops, right? If
Mhm.
A multiply A with A, you're gonna get 2 hops, right? And 2 hops extension of the graph, meaning that you're gonna connect any pair of nodes whose path has 2 steps, 2 hops, length 2. You do cubic means they're gonna connect all the nodes. They are connected, and their path length is 3.
Mhm.
And then they do the diagonal.
I think this one is for 4 and this one is for 5.
Yeah. And they also got Y6. So this is the feature, right? This is what they call this. This is called like structure features.
Yeah, this is the f of these are all the like they had the z is equal to f of g prime. This is all of those features that they were talking about.
Okay, so if you take a diagonal, they're not doing weighted graph, right? Their adjacent matrix is just like a 0, 1 matrix.
I think so, but they don't specify.
Okay, then x3, 4, 5 just means at least x3 just means like if you extend your graph by connecting all like 3 hops paths, what's the degree of every node?
Mhm.
And x4 is like, I don't know what x4 means. It's a little bit.
I think this is supposed to be 4 hops because they're concerned about how many k cycles does the node belong to.
Oh, okay. Up to 5 cycles. Okay. Um, okay. So Y3, Y4, Y5, Y6 are just the global features, right? Oh, those features are applied on every, no, not global features. Every node has this many features, right?
Yeah.
And okay, what's their spectral features?
Um,
Oh, okay. They do the eigen decomposition, right?
yeah. They only use it in experiments that have up to 200 nodes.
Oh, okay. That's kind of like global features
Mhm.
and molecular features. And then do they put these spectral features on every node?
I don't know. They might just input it in here, but I am unsure of how they do it.
Okay. And then they just do graph transformer, right?
Yeah, so they have this Grant's draft transformer for how they do it.
Are they do graph transformer only on the neighborhoods?
Sorry, what do you mean by neighborhoods?
I mean, graph transformer just usually means like you're gonna do self-attention um, um, with nodes. I mean, for every node, if you want to do self-attention, it just means like it's gonna look at all the neighbors of that node and then do that QQA and then
I think it's globally. It's with every other node in the graph.
oh really?
Yeah.
Zhitong, when you do the graph attention, um, how do you conduct the self-attention?
I think it's with the node that there is an edge that connected.
Okay. And then their Q is like the Q vector times dot product with the key vector across all the nodes, right? All the neighboring nodes and as well as
Yes,
itself.
yes,
And then do the weighted aggregation.
yeah.
Okay. Okay. Yeah. Yeah, looks like there could be a lot of tweaks here.
Right. Yeah, and the only last thing to sort of show is that they showed that having that using that marginal distribution or over the uniform distribution does have a slight increase in performance. And that they show that it also, if you include additional features, it can improve it a bit more.
Oh,
And this is all compared to Congress is if you were to use a isotropic Gaussian distribution for your definition of Q.
okay. This Congress is also like a graph generation, is a diffusion model or not?
Yeah, it's the exact same model. It's just that they've just defined Q to be a Gaussian.
Oh, but isn't Q is Q is transition? Okay, you mean that each entry comes from a Gaussian?
Yeah,
Yeah.
I believe so.
So it looks like the choice of the how do you sample Q and whether you add into additional features really matters a lot, right?
Yes. Yeah.
Okay, at least we know the whole framework. Seems uh our our plan should be feasible as well.
Yeah, I think it should be very doable.
Okay. Yeah, okay. Do you have any other thing you want to highlight for this paper?
Um, they proved the conditional generation for like how they're adding the input features. I only think that is important if we do diffusion in supervised learning, where we will need to basically use our input data set as a prior. And they show that you can't.
Oh, this is lemma 5.1, okay.
Yeah.
This is not their work, right? This is a
No, this is another papers.
conditional reverse noise in process.
Yeah. So this is another paper I have to read. But I'm basically just going off of what they presented here.
Okay. Yeah. Okay. Yeah, maybe we can look at another paper.
Mhm. Okay. So the next one is layer DAG. So this is in a similar vein as digress, only they are, instead of generating arbitrary graphs, they're only generating DAGs.
Okay.
They also are going to introduce autoregressive diffusion for these DAGs. So the important sort of observation that they made about DAGs in order to do this is that you can view a DAG as a bipartite graph, where if you have, let's say, your first layer of 4 nodes, you know that it is the existing nodes are going to be a bipartite graph with the next nodes. Um, so you would have arbitrary edges between the two. And then if you look at the third layer, you're going to use all the previous existing layers as a bipartite graph with the next layer. So any of these nodes in layers 1 and 2 can connect to layer 3.
Yes.
And so what they're going to do with that is they're basically going to say we're only going to perform diffusion 1 layer at a time. And we're going to, so that we can use the previous layers as prior information for the next layers.
Oh, so they perform like several generation
Yeah.
procedures.
But this allows them to also get rid of the arbitrary, like a finite number of nodes, because they are able to predict how many nodes they think should be in the next layer, which makes it so that it could have an arbitrary depth.
But the number of depths is determined by how many autoregressive steps you're going to use, right?
Yeah, yes, but you can they use 3 neural nets. So they use 1 to predict the cardinality of a layer,
Okay.
which I think is denoted, well, I think it's VNT. And then they have the X's and the E's as well. And so they first are able to predict the cardinality, and then they predict the value of, or the class of those nodes, and then they predict the edges of those that connect to those nodes.
That's for generating 1 next layer, right?
Yeah.
Okay.
And so this is basically how they set up their auto generation. So the basic ones are, they have the probability of the cardinality at layer L+1 is dependent upon their graph at all previous layers. They then have their probability of their node values given their graph at all previous layers and their cardinality. And then lastly, they generate their edges with it, which is done through this adjacency matrix A.
But isn't the adjacent matrix A also generated along with the
So in this case, they're not generated simultaneously.
so the first the first sample the number of the nodes, right, in the next layer,
Yep.
and then they generate the types of the nodes, the type for each node. Then they generate the adjacency matrix.
Yeah.
And how is each generation done? Is each generation is also diffusion? Is different diffusion?
So each generation is done via diffusion.
Okay, so I can imagine that the generation of the type of X is kind of categorical. It's kind of categorical generation, right?
Yep.
Is there
Yeah.
any rule in this process, or is it just apply the method in the paper you just mentioned?
This is all basically just applied from the previous paper.
The previous paper, you mean the Google paper? The
Yeah, this degress paper. Is this DeepMind?
No, this is not DeepMind.
Yeah.
Instead, this degress paper is using the method proposed by some like a Google people.
Yeah. Yeah, from Google Research, yeah. Yeah, this paper seems to basically just be building on it. But they've changed the architecture of their model. So I guess the important thing is that they have a encoder to encode the graph information, which they're training via they're doing bipart message passing neural net. Yeah. And then it gets after that encoder, it gets a bit weird with how they describe it. And looking into their code base, it does look like they have a different bipartite message passing neural network layer for every single one of these generators. So each one of these probabilities is generated by its own neural network, it seems like. And sorry, what?
Okay. But my question is that for CETA2, right, like to generate the class of nodes, since you have already known the number of nodes, right? Say it's just 10 nodes. What you need to do is just you need to generate the category for each node, right?
Yeah.
For that one, how do they do that? Is it like just a direct application of the Google paper? Because there's no. Oh, they also apply some transition probability matrix, right?
Yeah, they're using the same sort of methodology that Digress used, where they have some sort of noise. They have a noise that they've applied, and they're slowly recovering the graph. It's just that they're only recovering it one layer at a time.
Oh, okay. So for CETA2, the generation, like for the nodes, they use the sample the transition probability matrix for nodes. And the next one, the adjacent matrix, they sample the transition probability for the adjacent matrix.
Yes.
Okay.
And it should be stated that these aren't like it's they don't do very well in directly stating what adjacency matrix they're using, and they don't supply a lot of detailed information about this methodology, where they give a bit more details on their diffusion, and they basically just say we use dgress. We basically are just using dgress's methodology for generating each layer.
Okay.
I think it seems like the only real novel thing that this paper is doing is that they have, first off, they're applying this to DAGs, and then they're also doing this in a layer-wise fashion. And the reason why, and yeah, because of our research with expression trees, this becomes much more interesting because all of these expression trees we're generating are just DAGs.
Yeah. Yeah, we can think of like whether we're gonna use this layer-wise approach or
Yeah.
I'm not sure actually.
Yeah, so if we go to the results, so this is just of table 1, which I think sorry, I'm trying to figure out which data set this is. This is just basically logical constraints are placed on these graphs, and it's trying to just continually generate new graphs based on these constraints. So there's 3 versions of it listed. So there's a one-shot DAG, which is where they don't do any of the autoregressive training, and they just try to predict the DAG all at once. So this would be much closer to the diffusion version in dgress. They have a layer DAG where they only do autoregressive, so they only do one step of diffusion. So, and then they have layer DAG where they do both autoregressive and diffusion. And consistently throughout the results, it seemed as though layer DAG did significantly better than the one-shot or the single-step diffusion.
So why the layer DAG? I think a layer DAG should maintain the validity of the, or down here validity has other meanings.
Yeah, validity is, I think they're doing it by a hidden set of logical rules that the data set has to learn.
Oh, I see. So it's not just a structure must be a DAG.
Yes, yeah, it's certain like certain rules about node classes within the DAG.
I see. Yeah, that makes sense. Yeah, good thing is in our case is that even we are generating DAG, we do not need to generate the edges, right?
Yes, yeah.
Once you have the operator there, you know how many edges it will have.
Yes, the question then, yeah, we could then ask the question of, do we want to allow the graph to generate its own edges? Because that would allow for instance, like if we had like a plus as our root node and we were to generate, let's say, a sign token and an X token. I need to make this graph more complex, sorry. Or let's do multiplication. Let's do another addition. When we generate the third one of, let's say, what is it doing? Okay. So we now have a plus here. When we generate this third row, if we were to generate the nodes, let's say constant 1, x1, and x2, if we let it generate its own edges, it could learn like a sign relationship to x2 and a plus relationship between c1 and x1. Whereas if we used our rigorous rules, we would force the sign onto the c1 and the plus onto the x1 and x2. So having it generate the edge matrix would increase complexity, but also could increase flexibility of the model. So there's
okay, one thing is that I feel like it's more like if you just change the order, you have the same thing, right? The only
Yes.
the only thing is that you just allow the type, right? You can have like variety type
Okay.
because you have sign. You must you only have one edge. You must have some edge from sign to the next node. Only
Mhm.
one.
Okay.
Oh, but okay, but there is a still like suppose you got sign, you got plus, you got oh no, let me think about that. Is it possible like you have a minus sign? And sign becomes a multiply. Will they share the nodes?
You could allow them to share the nodes if we wanted. It could add for much more complex graphs. In this case. Because this could be like embedded, this could be a smaller part where there could be much farther stuff down below. But this is also an option. This is, I believe this kind of architecture, one other recent paper did something similar to this. But I don't remember them having a high degree of success, but I'll have to recheck the paper.
In our current paper, like in our CAD RSR, do we allow this? Like share nodes?
In our current one, we would not allow this. We have predefined edges and we make sure there's ample nodes that each edge connects to a unique node.
Oh, I see. Yeah, we can discuss about that.
Mhm.
Like if we use our current practice, then we even do not need to sample the edges. We only need to sample the types of nodes and also decide what's the depth of the DAG, right?
Yeah.
Okay.
All right. Are there any more questions about this paper? I think they will rewrite it and add some stuff to it, but for now it seems that is the only sort of notable thing I've seen from it. But it is interesting in how they break it apart into layers and make it so that they can explore to an arbitrary depth.
Okay.
Um,
But they haven't say how they select depths, or you can decide.
so the depth is when they predict the cardinality for the next layer, they terminate it if there are no new nodes in that, if they predict 0 nodes in the next layer.
Oh, I see.
Yeah. For our case, it would be a little bit different because we need termination nodes to end the tree. So we wouldn't we could predict cardinality, but we would need to enforce a sort of minimum or maximum number of nodes that can be generated.
Yeah.
All right.
And you mentioned that their network is based on what? On the message passing, the graph neural network.
So their implementation is a bit strange, but they basically use a bidirectional message passing neural network. And then they use a transformer, which I believe is just the encoder layer of a transformer. And then they'll use some sort of multi-layer perception. And that's it. And they add a bit of statement about a layer-wise positional encoding. However, it's very unclear how if they use it or not, because they say in their design, they say we then apply a transformer without positional encodings, and then they talk about layer-wise positional encodings.
Okay.
but in their code, I didn't see where they used it. But there is potential that they are adding in some sort of positional encoding information when they're sampling X and edges. So I guess this is actually a full transformer. They just use the encoder and then they use the decoder to no, I actually don't know. Oh, I need to double check that in their code.
Yeah, okay. It sounds good. Okay, maybe you can talk about the third paper.
Yeah.
It's pretty fast, yeah. It's good.
All right. So the third paper is a bit different. So this one is just focused on how do we train diffusion models for reinforcement learning. So this is all focused on image generation, and they're specifically applying their specific use case is that they have a pre-trained transformer based model that uses diffusion for sampling, and they want to improve the quality of it by either a new discriminator or by human feedback.
So the pre-trained transformer, where is this pre-trained transformer from? Or how it was pre-trained?
I believe it's just they used an out of the box. They used. Sorry, I'm looking for it. They just used an available out of the box image generator.
Image generator.
Sorry, see if I have it in the notes. I don't think I have it written down.
Okay, what's the role of the pre-trained transformer in his framework?
They say that they can use a pre-trained transformer or a non-pre-trained transformer, and they're basically using it here, where you're going to get a score, you're going to get a statement. You want to generate an image, you then ask a human or another discriminator what's happening in the image to get this, and then you then compare.
Oh, so the pre-trained transformer is served as diffusion model, conditional diffusion model.
Yeah.
Okay.
Yes. So they use Stable Diffusion version 1.4.
As the base model. Okay.
So there's a few things that they talk about in terms of altering the reward function for image tasks specifically. But the interesting part is how they talk about reinforcement learning training for diffusion models. So they introduced two reward rated regression models, where they are essentially using the reward at the of the final step in generation as the target, or as just the reward for reinforcement learning. And they also have a sparse version where they use a cutoff threshold. This is interesting because this would be very similar to how we are training CADSR with our BIC.
Yeah, but what's R? R is a
reward function.
Yeah, well, how do they define the reward function?
For their reward function, they're defining it as a discriminator.
I see. Okay.
Yeah. In all their experiments, they're using a discriminator that has like a aesthetic score.
Okay. So that means like R is also computed from some neural network, right?
Yes.
And And the discriminator is trained beforehand or jointly updated during the reinforcement learning?
For all of theirs, it's trained beforehand. And they don't do any online training.
One question, how did they train the discriminator?
The discriminator is a pre-trained version. I believe it's just lava. They use a lava and then they use the BERT to generate a similarity.
But lava cannot give us a score.
Lava is generating a description of the image.
Yeah.
And then they're using BERT score, which takes in two
Oh, I see.
descriptions and gives a similarity.
I see. So combining the lava and the BERT score, that is our reward function.
Yeah.
I see.
But then which parameters do they update? So they still update the diffusion model?
They are just updating the diffusion model.
Oh, I see. So the discriminator is actually fixed.
Yeah, I think it's the goal of this paper just like use a small diffusion model, and they can like kind of like combine the advantage of lava and BERT score.
Yes.
I see. Thank you.
Yeah, so the only thing we're changing here is we're just changing the diffusion model. And the goal is that one of their reasons for introducing their reinforcement learning method is that they want to use human feedback instead of lava and BERT score for images. However, getting human feedback is very expensive. And so they introduce a way to minimize the number of times you have to ask for either human feedback or for lava and BERT score.
Okay. So basically the diffusion model comes from like a pre-trained transformer, and then you're gonna update it further through this reinforcement learning framework.
Yeah.
Ah, okay. But we'll get human feedback. Will the human just give the description and then through the BERT score to get the reward, or human will just give the score, the whole score?
I believe the humans just give the full score.
Oh, okay. That means human give the reward.
Yes.
Yeah, that's a very simple idea, right?
Yeah,
where is this paper published?
I don't know if it's published yet. They do an additional step where they show that they have improved reinforcement learning I haven't introduced yet.
Yeah, if you could click PDF, if it is published, they should say this is published.
I think it's the iClear 2024.
Oh, I see. Is it accepted or rejected?
Accepted.
Accepted. Okay.
Yeah. So the big thing is that they do a denoising diffusion policy optimization now, where they're basically showing that you can train at each step of diffusion rather than just the final step based on the final reward and the current step you are in the process. However, they note that this requires a lot of sampling, and with calling additional models or asking for human feedback, that has a lot of cost to the reward call. So they instead show that you can do multiple rounds of optimization on a single sample by making sure that you don't diverge more than a certain distance away from your previous probabilities.
Isn't this just the like initial gradient?
Yeah,
Right.
yeah. There's nothing. Nothing about this paper screams extremely novel in terms of what they're doing. It's just it's nice in terms of how they show it, and their results seem very good in terms of we can see that this is sort of the new final one that they introduced, and it is able to learn much more quickly and stable than the other 3 reinforcement learning methods they show.
So can I take a look at how do they update the model? So I can imagine like every time they're gonna generate a sample, right? They say they sample noise and then they get noisy state, then they recover the. Oh, they just get p theta given xt minus 1 given xt. Is this guy come from the diffusion model?
Yeah, that should just be how they're optimizing the diffusion model. And then they're just scaling it by the reward that it would get at the final step.
Yeah. Okay, this one. So I'm a little bit confused here. X0, isn't X0 the sample generated by the diffusion model, right? Because every time when you generate a sample, you're gonna let the discriminator to decide the reward, right?
Yeah.
So I think it's not X0, right?
No, I think perfect hypothesis. I think the summation doesn't include the R. So only the first part is sum. The summation doesn't include R. So that we only have a reward at the end of our trajectory.
Also X0. Oh, okay. Also, it's pretty standard reinforcement learning. Okay.
Yes.
Yeah.
Okay. Okay.
Yeah.
Wow, okay. That's a little bit too costly, right? You're gonna track all the trajectory, the whole trajectory.
Yeah.
Then you multiply reward. Why don't they just like, for example, they sample they random pick up a step t, and then they generate a noise, and according to the noisy state and the t, you kind of try to recover the x0, and then you throw x0 into the reward. You got the reward and multiply that the gradient of the the gradient of the noisy network.
The only reason I can think of is because the reward function is too costly, where they're trying to minimize it, so they're trying to get as much as they can out of each sample.
Oh, so they want to look at the whole trajectory and then multiply reward.
Yeah.
Oh, okay. Yeah, but if they have the if I'm the third party reward function, say from the lava and blood score, if they can quickly get this, I think if you frequently retrieve the reward function, that will be even better.
Yeah, if you could do these updates much more quickly without having to do this. But interestingly, they show that you can doing more updates. I don't know how this reflects time, but because they're going to be doing multiple updates per reward query in this graph, so they're essentially updating much faster. But I guess each update's taking more time.
Okay, again, you mean for one reward they can do multiple updates?
Yeah, because of for each sample with this equation, the DDPO IS, they're able to calculate the gradients multiple times for each sample. So they, for instance, they could sample like sample 10 times, and then they could perform the optimization on those 10 samples, let's say 5 times, before they had to generate 10 new samples.
What's the rationale? Are they assuming that the theta old will have the similar trajectory and end result with theta?
Yeah, they're trying to use theta old to control the trajectory of your new theta.
Okay. Okay. Yeah, but I can imagine this could be pretty costly, training this. But because their diffusion model has already been well trained, right? They're based on some pre-trained transformer on that. That one has been well trained. So you add this additional reinforcement learning. The basic means like you don't need too many reverse query. It can help. Yeah.
Yeah. Yeah, I mean they're doing like basically taking like these pre-trained images and they're trying to form them into like a compressed image or something that's incompressible or something that has like a higher quality, where they're basically just trying to alter like quickly alter a pre-trained transformer to have some sort of different quality.
Okay.
I got one question. So for figure 4, the first graph, why are they going, some of the methods are going downward?
So I think this is because these two methods are RW sparse and RRWR. These are not training along the full path. They're just training for the given example or for the given sample.
Okay.
For a given sample, what does it mean?
They're like they're sampling the image. They're calculating the reward on the sample, and then they're doing just back propagation here, based on this reward function. Or yeah, based on these weights, where it seems like they're not actually using diffusion.
If they're not using diffusion, how?
Or, sorry, they are using diffusion. It's just that it's not theoretically justified. And it's just an approximation of to optimize this equation.
So DDRL. So what does C mean here? C is the language, this context. Oh, okay. So you mean how do they apply that? They just get reward weighted regression. You got this reward. I still don't understand. So basically you got this weight this is just the reward, right? They give the reward. Does it mean like you just use this reward to train to perform the reinforcement learning?
Yeah, I believe so.
So that means like this weighting approach doesn't work.
Yeah, it doesn't seem like it's working well.
Okay, so it's better to just use the discriminator output. That's the reward.
Mm-hmm. And yeah, and just to do the diffusion. Where yeah, it seems like it diverged with the aesthetic score, and then it had marginal performance elsewhere.
Okay. It's just a reward choice. Okay. Yeah, that's interesting. But my gut feeling is that you must have like a very good pre-trained transformer, right?
Yeah, it looks like for their pre-trained, they're generating very strong images already.
Yeah. Then you add some like reinforcement learning steps. You can further improve the quality.
Yeah.
In our So in our method is kind of like we should make our CAD-SR transformer to be some kind of like pre-trained transformer.
If we wanted to do this, so there, I think there's two, like if we think this is one way to do reinforcement learning with diffusion, but if we do end up switching it to a supervised learning, this might be an additional step to do some online learning if we find that our pre-trained diffusion model isn't performing well enough.
But online, you mean
Or
kind of few shots, right? It's like okay, I have already had some like a pre-trained model, and I have this data set. I do some reinforcement learning to further improve it.
yeah.
Okay. Okay. Yeah. Yeah. Very good. I think we got the idea.
Mhm.
Yeah. Yeah. Any questions from Zhitong, Da, Graph, and also Yile?
I think I'm good. Yeah.
Okay. Yeah. It'd be good. I think it's good. Right? It's very efficient, and I think you see those papers like the diffusion on categorical data. It's very recent work, right?
Yeah, this is 2023 of February.
Yeah. But why is published in 2021?
Oh, this might be the update. Yeah, it's 2021. Sorry. This is
Okay.
the update date.
Yeah, but I do feel like this is useful since the many tasks we're dealing with not only the continuous data but also discrete and also likely to be to be hybrid, right?
Mm-hmm.
Yeah, if we can leverage this kind of technique, or at least or improve those, there will be a much broader problems we can do.
Yeah.
Okay, great. Yeah, let's stop here today. Zach, you can think about. I think now you can think about how can we design our very first diffusion model in generating symbolic expressions.
Okay.
Yeah, and I will start looking at those papers as well.
All right. All right. Sounds good. Thank you, Shannon.
Yeah, thanks, and thanks for other the joining this. I think it's really useful. I think next semester I want to systematically organize this one. Okay, yeah, see you around.